We'll be talking about signals and systems in a variety of different domains this semester. In terms of time domain representation, in previous classes you talked about signals and systems in the continuous time domain. So this is the x of t, h of t with the parentheses notation that we were just talking about. In this class we'll talk about signals and systems in the discrete time domain. This is the bracket notation, bracket of k, bracket of n notation that we've been talking about. We'll also spend a lot of time talking about signals and systems in transform domains. So instead of talking about them in the time domain, we'll transform them into some other representation. This representation can give us insight into other characteristics of the signal or system, which is very useful. For instance, when looking at signals or system in the frequency domain, knowing the frequency content of the signal is a very useful thing to know about it. Some of the other domains that we look at, like the z domain for instance, that's something that we'll be looking at in this class, physically does not have a great interpretation of what exactly that is. It's really hard to think about what does a z-domain representation mean, but mathematically it really helps us simplify things and do some things that are more difficult to do in the time domain. So sometimes the transform domain does have a very physical, real-world meaning. But we know what frequency means. We know what it means to oscillate at a certain frequency. Other transforms are a little bit more difficult to wrap your head around, like the z-domain or the s-domain, the Laplace transform, things you've studied before. But they help simplify a lot of the mathematics, and because of that, they're very useful transforms and useful tools for us to analyze signals and systems. So let's go ahead and spend a little bit of time reviewing some time domain techniques and important time domain quantities. One of these is the impulse response. The impulse response of an LTI, continuous time system, is the output of the system at rest due to a unit impulse applied at t equals 0. So first of all, let's remember what LTI. LTI means linear time invariant. So if we had a linear time invariant system, when we were talking about continuous time systems, there was this quantity called the impulse response that was a very useful quantity. It turned out that the impulse response completely characterized the LTI system. If I gave you the impulse response, you knew everything that you needed to know about the system. Mathematically, we represented the impulse response with the notation h of t. So we saw this a lot in previous classes, whether being provided it, hey, here's h of t for this system, use it to do some analysis, or being given a system and being asked to find what h of t is. And the reason it's useful is because if you know the impulse response of your system, you know how to compute the output of that LTI system for any input. We know that they are related in the time domain via the convolution integral, and we'll get to that here in just a minute. This is a little block diagram of what it means to get the impulse response of the system. It's basically a graphical version of the definition we have. If we have a linear time invariant system that's at rest, and if we put into it an impulse, by definition what comes out of that system is h of t. So you can kind of remember the definition in words if you want, but this block diagram is the exact same thing. A linear time invariant system at rest, we apply an impulse at time 0. What comes out by definition is what we call h of t. Continuing talking about the impulse response, this chart reviews what we know about it when we're dealing with continuous time signals and systems. If we know the impulse response of our system, this is h of t, the convolution integral is what relates the input of the system, inputs denoted by x, with the output of the system. So this equation right here, this integral, is what we call the convolution integral, and it says if you know the input and you know the impulse response, you can compute the output of the system via this integral. And instead of writing this integral down all the time, we often use this shorthand notation x of t star h of t, which you read as x of t convolved with h of t. Instead of this equation, we can think of it as this block diagram. If I have some signal x of t, if I put it into some system, which is described in the time domain by the impulse response h of t, what comes out is the signal y of t. So we're used to doing this type of thing for continuous time signals and systems, and this math, this convolution integral, is something you practiced how to evaluate it, and you learned how to do that in previous classes. We have something very similar in this class for discrete time signals and systems. This equation right here is the analogous equation to this continuous time signal. It's not a convolution integral, though, because we won't be dealing with integrals as often when we deal with discrete time systems. It's called the convolution sum. It does the exact same thing as a convolution integral, though. It relates the input and output of a linear time invariant system. The difference is it relates the input and output for discrete time LTI systems. So it looks very similar. You give me the input signal x of k, which is a discrete time signal. You give me the impulse response of your discrete time system, h, and I can compute the output of the discrete time system for any time n that I want by just evaluating this convolution sum. Again, instead of writing down this summation all the time, we use the same notation, this star, x of n star h of n, to indicate x of n convolved with h of n. And the notation here, the brackets instead of the parentheses, tell us that we're dealing with a discrete time convolution as opposed to a continuous time convolution. So the impulse response of an LTI system is a very important quantity. It lets you know the output of a LTI system for any input, and by analyzing the impulse response you can also understand properties of the system, whether it's causal, non-causal, whether it's bounded input, bounded output stable, things like that. Another time domain analysis technique that you learned previously was how to analyze differential equations. So instead of representing a system with an impulse response, you learned how to represent a system with a differential equation. And you learned how to solve that differential equation to get the system output for some system input. So this is just another way of doing kind of the similar thing that you use the impulse response for, just in a different way. Often the way that you solved the differential equation was to use the Laplace transform. So instead of dealing with a time domain differential equation, you would transform the differential equation into the Laplace domain, into the S domain, and then you could just use very simple algebra to manipulate polynomials in S, come up with roots of those polynomials, and then transform back to the time domain to get the time domain solution that you were looking for. So you had a fair amount of practice doing that in previous classes for continuous time differential equations. We'll be doing something very similar in this class. So these two bullets here talk about what we'll be doing in this class. The difference is, instead of dealing with differential equations, which are time domain continuous quantities, we'll be talking about difference equations. So difference equations are the discrete time counterpart to differential equations. So not too long from now we'll start talking about and introducing what we mean by a difference equation. We'll have very similar objectives. We'll be given a difference equation and we'll need to analyze it. We'll need to solve the difference equation. Well, there are different ways to do that. One way that we'll find very useful after we introduce the Z transform is we'll learn how to take a difference equation, take the Z transform of it to obtain polynomials in Z, do very simple algebraic manipulations on those Z polynomials to actually solve the difference equation in the Z domain. So the process is very similar to something you've been doing before. Before, we had time domain differential equations, go to the S domain. Now we're going to have time domain difference equations, take the Z transform, go to the Z domain. So very, very similar process, just with a different transform, slightly different mathematics.